Okay, so I come to this formulas, all right? Under formulas, you see create from selection. You see I selected H and the point 1, all right?
Why is it 0.1 again?
Because I chose it. The problem said choose point 1.
Oh.
Okay. Okay, so that's remembering from what I had on the thing. So again, the things on this, you have a problem to work, you've got an initial condition, you then choose an H, and then we can iterate from there to get an approximate solution as far as we want. So that's what I want. Now, I've just put this 0.1 in here. It's just a choice. I could have put 0.5, I could have put 0.2, doesn't matter. But I want to go out. I'm saying, at this point, I'm saying I'm going to want to try to approximate the population at, say, 1, or maybe at 2. Okay? We already know what the solution is. So one of the things I could actually do over here, and I will do this as P act for actual. All right. Now, what am I going to put for T? I'm going to start by putting 0. What am I going to put for the first p-value? I'm going to put 50 in there. Obviously, the same thing for the exponential. All right. Now, what did I say? I didn't write this down, but it's a very important equation. I have that Tn plus 1 is equal to Tn plus h. We update the time by a new h value, right? So, for those who don't know Excel, you can watch what I'm doing. For those who do, what I'm going to write in here is equals what? The previous cell, that's the T0, right? And then I'm going to do plus the h value. All right? Yes?
I know you said it, but how do you define with h? You go to the formulas and you select those two, h and point 1?
I just highlight them.
You just highlight them.
You just highlight them, that's all it does. Yep.
Why is it A2 plus H?
So A2 is this cell here.
Okay.
So it's taking the so my new value
I got it,
is
I'm
the
sorry.
previous
Okay.
one plus h, right?
Yes.
And this is where Excel is really strong, is it's called updating things. And these are called updating functions. So this natural, any of your discrete dynamical systems fit really naturally into Excel. Okay. Now, question, yes?
Highlighting it doesn't do anything, it just highlights it. Like when I do plus h, it just says, what is h?
Well, you have to have defined it.
That's what I'm asking, how do you define it?
That was up here. Under formulas,
Okay,
create from selection.
that's what I was wondering.
Sorry, I guess I went too fast for you.
I just asked, like, I know you have to define it as in the formula.
And that's through the formulas thing on your, formula things on there is create. It's a very valuable thing to do in Excel sheets is you can define things and whoops, I didn't want point 1. I don't have to go back from square 1 and I can redo it. Okay? Now, the nice thing about Excel is we can update things, all right? And the way we can update it is, notice I've got sort of that white cross there. If I go to this lower corner, it changes into that black plus. If I click on that, then I pull down, okay, I can pull down a ways. All right, that should be good enough. Okay, I pull down to 2. So just, so, and then notice what happens if I click on one of these squares. Instead of double clicking, so I have to redo it. Notice up here, it says it takes the previous cell and adds h to it. That's what that says right up here. It would also say it if I were to click on it so it expands the size. Yes?
How does it know that you want to go the next one back each time?
That's the
instead of-
default
Okay.
in Excel. It defaults to the one above it.
If you had more things below H in that column, would it default to?
So any empty square is defaulted to be 0.
Why did the H stay fixed, but everything else got?
Ah.
It's an absolute reference.
That's because I defined h to be 0.1.
I think when you if you were pressing like create from selection, I'm not sure if everyone saw that. I don't know if I did either.
So
Is that how you did this?
I did highlight this,
Okay.
create from selection, and the default is in the left column.
Okay.
And I say, okay, I like that. All right.
Okay, thanks.
And by the way, you could put 5 parameters or 5 values, and default would be all of those ones through this. So you can create as many parameters as you want. And notice what happens. Notice what happens here if I just change this to 0.005. Everything updated, right? Okay, I don't want that yet. We'll do that in a minute. Let's go back to
I think this is gonna be a long video.
all right. And so, and that's the nice thing about putting the
Getting
parameter
sore.
there, creating the definition, is I do one change in that and suddenly the whole column changes. Now over here, what would I like to put in this C3? Well, I've got the formula here, don't I? That formula says, you start your formula by equals 5O times the EXP of 0.2 times, well, the T. And where is T? By the way, you could define this T here and then you could use T, but I didn't. So I'm gonna have to click on this one, close the parenthesis, and there's the solution. And once again, if I pull this down, it fills it all out. Pretty easy, isn't it? Yes?
Just typing in A3 or clicking doesn't make any difference to how it references,
So what if, when I clicked on A3, it grabbed it from A3. I could have told it to grab it on A1, and then it's gonna give me the wrong answer, but it would work. And then what does it do? I'll double click on this so you can see it. This one tells me it grabbed this one over here. And didn't I want to grab this one?
I get that part. I meant like, does like clicking to select versus typing to select change it at all? Oh.
This one isn't any selection here. This is just using the one on there. If I named my variable t, I could just put t's there, but I didn't. Okay, now should be just as easy to put in Euler's method, right? What is Euler's method? It equals. What does it equal? It equals the previous p-value. Where's the previous p-value? Right above it. Then what do? I add. What do I add? The h times, right? What? I'll put quantities around here. 0.2 times.
One next to it with above it.
Okay.
Diagonal.
No. The Euler's method gets it just from the one above it.
Oops.
It's the Pn. So it's P1 is going to get P0 and P0. Now, you're actually showing me a common mistake that students make, which is to go to the exact solution and get it. But remember, a lot of these problems are not going to have exact solutions, right? So all we can do is get it from the previous one, right? And then close parenthesis, enter. And then what am I going to do with it? I'm going to pull this one down also. All right. And now we can see we're about 0.3 off by the time we computed these problems. Let's look at the problem at 1. At 1, we're about say 0.06 off, right? Now let's see what happens should I go up here and I change this to 0.05. All right. Everything in the chart updated, right? I didn't have to do anything new. Everything's updated. But now if I want time 1, I'm down here, not up here. and I look at here, and how far is it off there?
Very little.
7. Alright. So before it was like 95, right? And now it's point, I don't remember what it was, but it should be half the error. Okay? So, was that pretty easy to do?
Yeah.
Yes.
Is there any a time that we, you know how the exponential one was a little more accurate? It is, right?
The exponential one is the answer.
Okay, right. So is there any time we use Euler's method over Euler's method over something else since the other one is more accurate?
What I'm telling you is that suppose you have an f of ty that you don't know the solution to.
Okay.
Then you can use Euler's method to get an approximate to it, but you have no idea what error you got.
Got it.
We have no idea what the error is. I would get approximations to that by doing, what did I just do? I have the step size, didn't I? Having the step size gives you an idea of how close you are on this. Yes?
So, I know the smaller the step size, like the better the estimate. So like, what do you, I mean, you're not done. I'll just wait.
So,
Because like you could
the
put
point
point
is-
zero zero zero
So
zero
what I'm
one.
saying here is, what happened when I did this? I had to do twice as many calculations, didn't I? To get down to 1. That's not cool. I have to do twice, to get to 1, I have to do twice as many calculations with half the step size compared to the 0.1. The 0.01, 0.05 is, to get down to 1, is twice the number of calculations going through this iterative loop as it was with doing h equals 0.1. Took me 10 steps on this one, it takes me 20 steps here. Now I'm getting a more accurate answer, but the cost was I did twice as many calculations. All right? Now the further cost is that every time, computers are not continuous, are they? They're discrete. Each time you do a calculation, there are round-off errors. Not too significant on this problem, but you get round-off errors from this. So the more calculations you do, the more possibility that error introduces into the system. Yes?
So if you had like a perfect computer that could just calculate anything to infinite precision, could you use this method to get accurate answers?
Technically, yes. If you wanted to have it compute for infinite time, because you'd have to do infinitesimal time. This method, as I mentioned, so one Michigan researcher lost $2 million because he wanted to use this method on an enzyme kinetic system, which is known as a stiff system, by the way, a particular system. When I got that to review, $2 million out the door. Didn't even have a chance on it. He got a poor review. Yes.
So since it gets more accurate with the smaller step size, but error also accumulates, is there a h value, a step size that is the most like?
No. Well, yes, no.
That is the most
question is,
accurate?
there is always a balance between step size and round off error.
Right.
And it's it's sort of a curve that looks
Right. So how do you
We'll show
find
it.
that?
You don't.
You can't.
You can, well, I can't say you can't.
Is there a
Well,
way
I
to
don't
start?
know.
Is there a way to visualize it and find that curve where it start?
No.
No.
I don't know how to do it. CS people might know how to do it, because then you have to start getting into the guts of the computer.
Mm-hmm.
How is it doing its round off? That's a whole different problem. It's a problem we talk about in numerical analysis courses. We used to, I don't know if it is now. But that's a much harder problem, and it's in the guts of the computer.
So we just find a step size that's okay.
Well, this is what I'm talking about is, this is a theoretical method. Let's stop right here, stop him right now. This is a theoretical method that works like crap.
Okay.
We do not use it unless we have to use it.
Okay. I'm fine. I'm fine with that.
Unless your test question says you must do it, you don't do it.
Okay.
all right? And this is where the 542 course comes into play. There are much better methods, and we'll talk a little bit about that when we're later here too. So this method, I think everybody agrees the Euler's method is A, simple. B, the theory matches with what you learned from calculus, all right? And so it's easy to implement, we can do it. Whether you should do it is another question. And there are lots of, we had some things in the existence and uniqueness thing. In particular, a lot of you just sort of, you glazed over, and I said it was fine to glaze over, that we had to worry about the partial of f with respect to y. And if that partial with respect to y gets pretty steep, we got problems in convergence. If you got problems in convergence, what good's the Euler's method gonna be? It's gonna be crap. Okay? So the point is, there's a lot of judicious understanding of what you use on these. And that's more of an art than a science. You have to know some information about these things. We can't do all of it. All right. This looks okay here?
Mhm.
Euler's method? All right. So,
Bless you. Maybe.
okay. So all I did there is so I've got some of these steps. And by the way, when you're doing this, if you were to have to do one of these on the final, which there's a moderate chance you'll have to do it, it's easiest to set it up as two columns here, just like I did in Excel. Doesn't this look exactly like what the Excel did? I just set these columns up. And then, of course, everybody bungles the arithmetic with their calculators, and I have a nightmare figuring it out. So these are not fun ones to grade. But does everybody agree this is a simple method to do? It really is easy, it's intuitive, and so, yeah, we can get these solutions, we can create graphs on them, and so forth. Okay, so we saw that for this particular one, I got to time t equals 1, we only had a minus 0.2% error on this. It is undershooting it, right? Because the exponential is concave upward, so the slope is always missing, right? So it's always dropping, the actual solution's always going to drop down. That's why we get that minus error. By the way, the error is always going to be what? 100 times the numerical error minus the exact solution divided by the exact solution, if you've got the exact solution. Okay, all right. Here shows the same problem, but P of t, the beautiful exponential growth is the blue line. Here I'm now going out to time 10. I show you the difference between using a 0.25 and a 0.5. All right. And again, I could drop it down to 0.1 and what? It'd be even closer. But then by the time 0.1, that's 100 steps out there to get to 10, isn't it? Would you love to do that by hand? Okay, these really are computer problems. Now, one thing you should sort of see is, pictorially, when I do the step size of 0.25 versus 0.5, isn't there sort of like half the error? So I drop the step size in 1/2, the error drops by 1/2. That's called order H. Order H is not. That's why we don't use Euler's method. Yes?
So, like, theoretically, I guess, if you made the H like 0.0001,
Yeah.
and
It would match
be
it.
accurate, right?
And especially, it's never accurate.
Oh, it wouldn't be more accurate?
Oh, it'd be more accurate.
Sorry, yeah.
You use the word more, I will
Yeah,
accept that. But it's never gonna be accurate, because what? The true derivative is the limit as h tends to 0. We're doing a discretization of that, which means we're truncating it.
Oh, okay.
And we're gonna see that truncation in just a minute, and that's why it's critical to the error analysis. Yes?
So what is the actual solution? Do you just plug in H? No, I understand. No, I understand. I know the actual solution, but if you're doing Euler's method for an approximate, pretend like we don't know that. Then we would just take our H value and plug it into the P sub n plus 1 and T sub n plus 1?
Yeah, so we had the general formula. So the general formula on this, I'll put it over here. The general formula for the first one that I have on the top line is yn plus 1. Again, yn plus 1 is equal to y at, is an approximation of y at tn plus h, is going to be equal to the previous y value, right?
Mm-hmm.
Plus h times f of tn yn. That's my general Euler's formula. It's on one of my earlier slides.
So then we just plug in our h value and then our tn.
You have to grid up your t's, which are based on the h's, and then do your functional evaluations. We'll do some more.
Okay.
Okay, the next example will be a little clearer on that. So again,